right, guys, welcome back for our final installment of the CEDIA webinars. This is our third day final presentation. It's going to be about loudspeaker specifications, how we could get more useful information. We've got a big panel here. I've never had this many people on a live stream before, so I'm sure there's going to be problems with interference and people talking, but we're going to do our best to keep it as clear as we can. We're going to give each person about 2 minutes to respond to whatever questions are asked. And first, I want to thank everybody for participating. We got Shane Rich from RBH Sound. We've got Dan Roemer from Perlisten. We've got Dr. Sean Olive from Harman. We've got Anthony Grimani, of course, and we have Scott Orth from Polk Audio. How you guys all doing?
Pretty good.
Just peachy.
Great.
Excellent. How about you, Gene?
I'm a bit exhausted, but probably not as exhausted as you, Anthony, because you've been talking nonstop for 3 hours, man. I don't know where you get your energy. I don't know if it's this chocolate or what you're doing, but I want you. Oh, there you go.
It's this chocolate. It's this chocolate.
But it says sugar-free. Don't you need the sugar?
No. This has got monk fruit. It's amazing.
Oh, monk fruit sugar. All
That
right.
does sound good. That's actually healthier for you.
Yeah, it's good.
Yeah. So,
those of you who don't know, I got to pause. This is really important. Those of you on this panel that don't know, Gene and I are serious chocoholics. Serious. We both have an addiction. We know it, and that's okay.
Yeah, I think some of the people on this panel also share our chocolate addiction. I know Shane and I have spent many times calibrating room systems, eating lots of chocolate, mass quantities of chocolate.
He just keeps pumping me full of it, and that's how he keeps me up at night.
Yeah. 3 o'clock in the morning.
His hours.
Yeah, I do. I work banker's hours for sure. So the purpose of this, I want to quote somebody that's been a great educator throughout the years, Dr. Floyd Toole, as Sean Olive is very familiar with. He once said to me, you get more useful information off the sidewall of a car tire than you do out of a loudspeaker's manufacturer's website. And, it's funny when you think about it, but it's also true because you can get a lot of good detail off the sidewall of a car tire, and you can't when you go to most loudspeaker manufacturers' websites. Wouldn't you guys agree?
Yep.
Yeah.
Absolutely.
Yeah. We need to start speed rating our speakers.
Yeah. Ours go to 180.
Yeah. So the goal here is, this is our initial discussion about how we can make this more better for consumers. But I would obviously like to have you guys back as guests to do follow-ups. I know, Anthony, you're doing a lot of work behind the scenes about coming up with a specification standard that all manufacturers can follow. And I'm hoping we could touch on some of these points and get all you guys feedback on this so we could come to some type of agreement on, what a good practice for doing specs is.
Right. It is about a practice. So the thing you mentioned behind the scenes is within the CEDIA organization, the expo is on its final minutes as we speak. There's a group of us starting about 3-4 years ago that have been coming up with a menu of the things that are needed by a designer, by a user, by whoever, of specifications of things that matter in terms of sound quality or sound functionality that should be revealed, that should be in a spec sheet, and that, like you said, there's more on the side wall of a tire than that. And so the group, it's called RP1, addresses speakers, but also amplifiers and projectors and screens and all the things that have numbers that you need to know when you're picking a product. And it's really a voluntary effort. It basically says, yeah, we all agree that we're going to tell people about this and that and that and that. The presentation of it's not a marketing document. It's a kind of an engineering specification. And in the case of speakers or amps, very similar to what you will already find in manufacturers that are doing commercial or pro products. You look at the spec sheet on most commercial speakers, and there's a bunch of really cool information that you go, this is the kind of stuff I need when I'm designing somebody's home cinema or somebody's sound system, whatever. So it's out there. It's not new. It's just arranged in a way that makes sense for the residential side.
Awesome. Yeah. So you have a slide presentation that you kind of want to just use to get the conversation going, talking points, if you will. I'm going to share your screen now.
Yeah.
And then we are going to also show ourselves. So, because I know you talk with your hands, I talk with my hands. We're Italian. So
I'm Italian, Grimani.
Yeah, you got to have a bit of both.
And just to be clear, Matthew Pose, who's with us today, is not actually sleeping. His screen is, he's outside in his car, and his It just froze in that position where he looks like he's meditating.
So he's having power problems
Yeah.
in Sarasota. That's why he's in his car right now.
Yeah.
He's dedicated, wants to be here with us.
So what are we here to talk about? This webinar is intended to guide speaker selection decisions. This is basically, at the end of this, you'll know a little bit more about what kind of things you should be getting or looking at in a spec sheet to go, that's the right thing for me, that's not the right thing for me. We're going to talk along the way about the importance of something that Floyd Toole, you mentioned Dr. Floyd Toole, has really focused a lot of energy, which is sound power, the net response of a speaker in the room. And I'm with him on that. Sound power is really important, and it's never, ever discussed on residential and not that often on commercial speakers. We're going to talk about sound pressure level, coverage, and other specs that are things that could be revealed because most people don't know what to look at or what they mean. So a little bit about who's here. I'm Anthony Grimani. I have these 3 companies. I make speakers, Grimani Systems, PMI Engineering designs rooms, and Sonatus Acoustics sells acoustical treatments. I've been doing this for 37 years all total. I worked at Dolby for a while, THX for a while, and 22 years ago, I left all that to start my own company.
Yeah, how old are you, Anthony?
How old am I? You really want to know? I'm 59 this year.
Wow, man! Congrats.
Thank you. I got another year to go before I can collect all my checks or something. I don't know, or 5 or 6. Anyway, Matthew Pose. Put it off. Keep going. Matthew Pose is maybe back with us. I'm not really sure, but he's he's a doctor with a minor in statistics, courses in acoustical physics, a very good practitioner and designer of acoustical things. He's been working around the industry for 20 years and 3 years as a reviewer. So he does review product, talk about it. Very smart guy. Now we also have, I hope I'm covering everybody here. Dr. Sean Olive from Harman is with us. In a few words, Sean, anything you want to say about where you've been, what you do, what's cool about you?
Sure. Well, I started my career at the National Research Council with Floyd and worked, basically had him as a boss at NRC and then Harman for, 30 years. And in the last, since he's retired, I've had about 10 bosses, but one every year.
Note that it took 10 people to replace Floyd, right?
Yes. Yeah. I fired them all. I just keep firing my bosses.
Nice.
So, but anyways, I've been doing research in loudspeakers, perception of loudspeakers and measurements and listening rooms and microphones and more recently headphones. So that's it.
Thank you for being with us today, Sean.
Thank you.
Your input's going to be invaluable. Scott, tell us a little bit about you.
Well, I've been in the industry for almost 30 years now.
Scott, your microphone's a little quiet. I don't know if you have a gain control.
I do, but I've been cranking it up.
Yeah.
We need 6 dB more at least.
If I had it this loud when I teach my class, it would be blasting their heads off. So I don't know what's up with this streaming service, but is that good enough now?
That's good.
Okay.
Okay. So I've been at this about 30 years now. I started in automotive audio at Delphi and did that for, I think, about 8 years, and then managed to escape automotive audio into home loudspeakers at Polk, and I've been there for 21 years. So, and I design everything from home loudspeakers to custom install loudspeakers, headphones when we were doing headphones, all-in-ones, the whole gamut.
Awesome.
Great. Well, thank you for being with us. It sounds like you have a ton of experience that's going to be valuable for this discussion. Shane, tell us about what you've been up to.
Oh boy, what haven't I been up to? Well, I'll tell you this much. I've been to Gene's house like 3 times in the last 2 months, and I'll be going again in another week or 2. So, but just to give you a little bit of history, I started with RBH Sound 27 years ago. Really kind of came in to the industry just as an avid lover of music, a do-it-yourself speaker designer, and I ended up getting an engineering degree And I really like to also credit the fact that I've been a musician all my life, and I love, not only do I love sound, great music, but I like to hear things accurately. And I think this discussion we're going to have is really going to be helpful to kind of pointing out some of the things that the average person really should know about speaker systems that will help them make decisions on what will work best for them.
Absolutely. Absolutely. Well, thank you, Scott, for being with us. And I look forward to hearing the next iteration of your visit to Gene's place. Dan, thanks for joining us today. Why don't you tell us a little bit about your background and what you're up to these days?
Yeah, thanks for having me here. Yeah, I'll say 25 plus. We'll leave it at that. Years experience. I'd have to do the math. My background originated from a lot of transducer specific designs, looking at the very detailed elements, material properties, modeling, doing a lot of magnetic simulation, frequency analysis, motion study. And then as years goes by, I did a lot more system simulations, designs. So I've had a lot of ground up experience. And that's kind of just continued to expand. Started doing a lot of the 3D work probably 15 plus years ago, simply because that was the engineering flow where you could go from, sketch to 3D. And then now with the packages, that the multiphysics packages you have, you can go right into a lot of the cool simulations. And then now tying that into, outcomes for, directivity response, things we're going to be talking about today, how speakers will sound, how speakers will react. So a lot on the technical side. And the other side of what I've been doing is consulting in all those categories for a lot of different brands, which has kind of given me a neat large experience with a lot of different individuals, a lot of different ideas, and a lot of different products over the years. And just recently, the last year plus, we started Perlisten, our own brand.
Very good. Well, thanks for being here. Very appreciated. So with this illustrious panel of experts, really people who know their stuff, we're going to talk about some of these things. Depending on the order, it's kind of interesting. I like to think that when you're trying to pick a speaker, the thing I always say in the CEDIA group when I'm leading this committee is, okay, the way this is all going to look in the end, you're going to have a bunch of spec sheets that all have the same formatting, and the thing at the top that I think is the first filter in picking your speaker is SPL capability. How loud do it play? This is the equivalent of saying, how much horsepower does this engine have? Is this the right thing for what I need to do, either to go really fast or pull a lot of horses in a trailer, whatever. So we're going to talk about SPL and how do you define that? We're going to talk about axial spectral response. We're going to talk about off-axis spectral response, globalized to sound power. We're going to talk about directivity. We're going to talk about distortion, impedance, and sometimes we're going to talk about profit margin. And sometimes profit margin is what drives the decision on selecting a speaker system into a room, and that's, I understand you got to run a business, but that's not necessarily the best thing for the client. I guess the best speaker is one that has great grades and all of that, matches the need, and has high profit margin, right? So let's talk about the first thing, SPL capability. So what we are told now, so if you try this exercise, you go online and you look at about 20 different loudspeakers from different manufacturers, and you download their little spec sheets or whatever, their brochures. On the consumer side, I'm not talking commercial, I'm just saying consumer brands, you're usually going to be told the recommended power. They used to actually say maximum power, but most times I'm seeing things that say recommended power from 20 to 250 watts. Most often it's going to say sensitivity. Not always, but it'll say something about the sensitivity. And is that enough to give you data about the sound pressure level capability of a speaker? Does that, if you're doing some either as a designer, you're trying to design something within a few decibels, or as a user, you go, look, this is what I'm trying to do. Is that enough? So I'm going to open this up and going to go, you guys, do we need to change that? Is that okay? Is it just okay to know what's the recommended power range and the sensitivity? Anybody have any opinions?
So we could start, if you guys want to go in order, just start with Shane and then just work through how the chat window shows each of us.
If everybody sees the chat window the same way, that's perfect. Yep. So Shane, what do you think? Is that enough?
Well, it's the norm, of course, but I think that there could be more for sure. We talk about sensitivity, and even that, of course, is not standardized. We talk about using a 2.83 volt sensitivity rating at 1 meter. And that's somewhat standardized, but then you have the 1 watt power rating, and that's confusing, I think, to the average consumer many times. Just trying to make sense of the difference there, if it's an 8 ohm speaker or 4 ohm speaker, how that relates. The other thing I would say about that, sensitivity, a lot of people, at least I commonly hear this, they mention that, they talk about how loud the speaker will play, or we do as loudspeaker designers and people in the industry, and we give maybe a maximum SPL rating. Let's say it's 115 dB for a speaker. Well, and people mistakenly think that that is the level that they are going to hear at their listening position, versus how it is rated. Those are some things I think we could expand upon, maybe better define.
Okay. So thank you, Shane. Dan, what's your opinion? Pause real quick. Shane started off by saying, well, this is what we're told now, or however we use it. Is that enough? Should we just all go home, not worry about it? Is that good enough? Do we need to go further?
Well, more is always better, right? More to a point, as long as you present it properly. But so looking at 2.83 volts, that's great, because nowadays you consider the amplifier voltage source, and then speakers, the impedance can vary wildly. So calling a speaker a 4 ohm doesn't really mean anything, or an 8 ohm anyway. So standardizing on a voltage makes a lot of sense. And then no matter what speaker you put on it, you're putting the same voltage source, and then that sensitivity has some true meaning to it. And then I think the other thing, when you say sensitivity, there's the days of speakers with ragged responses. You might pick the highest peak, and that's my sensitivity. Well, there probably should be some bandwidth associated with that specification, right? So is it in the mid-range, or is it a broader 100 to 10K, whatever it is, but adding some bandwidth to that spec makes it more meaningful. So now that speaker has to reproduce that SPL at 2.83 volts across that bandwidth. That gives you probably a good insight now where it starts, and then I guess that leads into what's the peak SPL capability. So when you talk in music, I like to think a lot in terms of peak capabilities. The RMS is kind of a tough one to define in terms of music, but the peak, that's going to relate to now the sensitivity of the speaker, and then what it can take for bursts, and that's a lot of how the music is being presented to the speaker anyway. Then measuring that, capturing it, defining limits, that's where you kind of open the next couple layers of the onion.
Right. And it is layers of the onion. That's a great definitely way to put it. Yeah. All right. Thank you, Dan. Sean, what do you think? Is it enough to just say, well, here's the power this thing's supposed to run it, and here's the sensitivity?
Yeah, I mean, I think I agree with Dan's point about the bandwidth has to be defined over which you're calculating the sensitivity. I just measure a headphone from one of those freebies from Air Canada that I had to use, and I brought it home and measured it.
I saw that.
Yeah, it was basically a single peak at 500 hertz, and then it was a bandpass filter. So at 500 hertz, it had this sensitivity, but above and below it was completely dead. So I mean, that doesn't happen much with loudspeakers much these days, but it has to be defined. The other thing I think when you talk about how loud a speaker will play, you have to consider the room volume and the acoustical treatment. If you're playing it outdoors or in an anechoic chamber or a very well damped room, you're not getting the contributions from the off-axis reflections. So I think somehow that has to be considered and standardized when you're defining how loud it'll play in a room. And of course, someone already mentioned the distance. Well, it's usually defined at 1 meter, but not many people listen at that close a distance. So that has to be taken into account.
Right.
Hey, Sean, quick question for you. So regarding sensitivity, is Harman still basically using the 300 to 3 kilohertz bandwidth for that type of spec?
I think so, but I'm not certain. I mean, that was more or less what I think that goes back to Floyd Toole at the National Research Council. They calculated the mean sensitivity sort of over the voice range from 200 or 300 hertz up to 1K. So I believe that's what we do, but when we define specs, it goes through the marketing department and things could change.
Understood.
I mean,
nothing like brutal transparency and honesty.
Yeah, we used to
profit margin gets added in.
We used to have a guy who ran our multimedia division, and his name was Mike Watts. And when we were defining specs for media speakers, I said, "Are those real Watts or Mike Watts?"
That's great.
Yeah.
Excellent. Thank you, Sean. Next, are we going around in a circle, Gene?
Yeah, I think Scott's
Scott,
next.
you're next. What are your thoughts? Is it enough to just say, yeah, this thing can take 250 watts, we're good?
I don't think so. I mean, there's so many. I think the first thing that I would argue is that you need to look at it from an application standpoint, right? There's different applications for everything, right? So does it just in general?
I'm going to pause you one second.
specs,
Gene, are you hearing Scott as quietly as I am still, or
am I still quietly doing
He's definitely got the bass turned up. He's not meeting the in-room target curve.
low frequency filter going? Okay.
What's going on?
Yeah, just a little louder, please.
Yeah. Well, I'll speak up.
Great.
Is that better? No, I sound like I'm yelling. Okay. So I forgot where I was, but anyway, you need to take into account the application for whatever it is, and that's just general for specs. But for this one in particular, I agree with a lot of what's been said. The definition of sensitivity is very vague. If you go out and look at websites from different manufacturers, which I have to do when I do competitive assessment, they're all over the place, right? And a lot of times when specifications are stated on a website, it's who's the closest competitor? Okay, add 1 to that, and that's my sensitivity, right? So there's no accountability for specs in general in a lot of cases, and that makes it difficult to either tell the truth or compete, and we can get into that later. As far as what could be useful is certainly sensitivity, and you could measure it 3 meters and back calculate it to a 1 meter 2.83 volt sensitivity. That would be perfectly fine. Or if it's a small speaker, 1 meter is fine. But if it's a larger speaker, measuring at 1 meter is not going to give you a real accurate measurement. In terms of power, on a lot of our stuff, we have like this range, and the range that we put in there, on the low side is basically how much power we think you need given the sensitivity of the loudspeaker to get to a normal listening level in a typical room. So taking into account that you're maybe 3 meters away and you've got 3 dB per doubling of distance in a room, how much you have to be able to put into this thing to get, I think we use something like 85 plus 6 dB of headroom. What do you need? How much power do you need for that? And that's the minimum number. And then the maximum number is based more on what's the peak capability of the loudspeaker, right? So we don't want to tell somebody, yeah, it's okay if you use a 1,000-watt speaker and get calls from customer service every day going, oh, you told me I could use 1,000 watts and, you know, I put a sine wave in and now it's trash, right? So there's this delicate balance. And in terms of loudspeakers, there are two basic limiting factors. There's thermal, right? When's it going to burn up? And then there's mechanical mostly. I mean, yes, there are some electrical things that'll keep it from stopping, but there's the peak, the mechanical part. When's it going to reach its limit of excursion or whatever? And those two things would be very useful. But, you know, nobody's going to know what to do with that.
Right.
So I don't know where you go.
So, Anthony, one thing I want to bring up is I haven't heard anyone talk about this. Yeah, we should have a bandwidth specified for sensitivity. I think the IEC does from 300 hertz to 3 kilohertz usually. But then there's manufacturers, I'm not going to mention any names. There's one in particular that always comes to my mind because when we measure their speakers, their sensitivity rating is always about 5 dB higher than reality. It's because they spec it in eighth space, but they don't tell you that on their website. They don't measure it in free field. They actually measure it as if there's 3 surfaces adding to the sensitivity rating. So what do you guys think about that? Shouldn't this be done anechoically at the very minimum?
Yeah, I mean, I think so. You need to define the space in which you're measuring it, and anechoic makes a lot of sense since most speakers are designed and tested in anechoic spaces.
All right. So just to be clear for the listeners, there is anechoic, and then there's whether you assume the speaker is on a boundary or on, you know, next to 2 boundaries or next to 3 boundaries, which could still be anechoic. You could still put it in the corner of a space like that and do that. So ideally, what we all need to do in this industry is all declare our things the same way, so that a pound is a pound, so that a meter is a meter, and it's all standardized. And in the end, you end up competing with everybody at the same footing. So now you can justify why your more expensive speaker is more expensive, as opposed to what the marketing person writes, which is the transparency is improved. Like, what does that mean? But if you can go through a series of things that clearly shows you these simple numbers that go, oh, I see why I'm spending $300 more for this version. That's really cool. And you may not need that extra $300, right? You may just like, you know, this, whatever that issue is not useful. So absolutely, when it comes to sensitivity, defining what is the measurement condition. So that's a lot of what matters. So I wanted to bring this thing up. My opinion is recommended power and sensitivity is clearly not enough, because that could mean just about anything you want it to mean. For all the reasons that everybody brought up, is there's different ways to measure the sensitivity and power, but ultimately the user doesn't care how much power they're putting in here. They care how loud it plays. And it's a very loose connection between those. So let's remind ourselves of this, that when we're talking about home cinema, this is a repeat of what we just covered in the session before. When we're talking about movie applications, there is a standard for how loud things should play. This is a picture of one of the mixing rooms at Skywalker Sound, up at Skywalker Ranch, just about 10 minutes up the road from here. There are standards for how those are built and how loud they play and all of that. And what we want to do for a client when we're designing a room is be able to play the sound level in here up to all of the peak and long-term requirements that are known and defined without overloading, unless the client goes, I am never going to listen that loud. Well, how loud are you going to listen? Well, I don't know, just quieter. Well, you can actually bring that client into a listening room that's calibrated to that reference and give them the volume control and go, let's watch a few sections of movies. Here's the volume control. You set it where you like it. And you can observe that they're 6 dB down from reference. Okay? You're never going to play any louder. No. Then that person needs a quarter of the power, much smaller speakers. Everything can just be a lot more modest. Now, you can still sell them the big speaker if they want headroom and capability once in a while to crank it up. But there's a way to trace honestly the client's needs to the size of the system and the capacity of the system. And that's kind of my little dream. Now, in a mixing room, each one of the 3 speakers should play 105 dB bursts. They're often known as peaks, but peak is confusing because it'd be half a peak to peak, just bursts. Average levels, if you actually look at what's mixed and how everything is done, there's like a long chain of measurements that explain this. The averages are typically 100 decibels per channel for the screen speakers.
Is that at the listening position or 1 meter?
That's at the listening position,
Gotcha.
at the mixed position. Everything is calibrated by setting by analysis and SPL measurement for a certain reference level to generate, really in this case is actually 85 dB of average level, and the burst can go up 20 dB up from that, and it's all standardized. This has been like a standard for 40 or 50 years. And so when you talk about home cinemas, it's a little different from music, but when you talk about home cinemas, there's a way to trace it down and give the client what they want. When you get to music, it's all over the board. You know, is the person just a lover of chamber music? Well, that stuff is never very loud. Are they a lover of really loud rap? Well, that's very loud. There's a lot of low frequency, and that's highly variable. And depending on the track, it's all over the place. But at least when it comes to film, we know we want to be able to do this with the screen speakers. We want to be able to do 102 dB bursts in the surround arrays. The immersive speakers, the ones that are usually on the top, it's 99 dB maximums. And the subwoofers, the low frequency, needs to be able to play 115 dB. And if you know some elements that we're going to talk about here, you can actually get there. So I also want to remind everybody, this is not always it's not thought through, but if you actually look at the average power, not the burst, but the average energy over a bunch of different film soundtracks, if you actually were to bin that, just kind of go, well, how much energy is going on here? The center channel is the loudest channel by about 3 dB on average compared to the left and rights, which is twice the power. And I see very often systems in which there's big left and rights and a little puny center channel where people go, well, that's just for dialogue. We don't need to worry about that. It's like, wrong. What's in the center channel is everything that matches the middle part of the movie, and it could be really loud. The bursts could be really loud, but really the long-term, if you want to think of it, energy, thermal power over time is the loudest. Then the left and rights are 3 dB down. The sides are typically 3 dB down from that, and the backs are 3 dB down from that. The immersive layers are about the same as the backs, or even quieter. So if you know all that, you can actually go, okay, well, I need a center speaker that can play this loud, and the left and rights that can play that loud, et cetera, and design intelligently. So,
hey, Anthony, I had a quick question on that.
Yep.
Is that like duty cycle, or is that actual loudness?
That's actual. Think of it as long-term loudness. This particular set of measurements was just measured by doing bins on RMS values of what's coming out the surround processor for the center, the left and right, et cetera. So it's a long-term root mean square average with long averaging.
So Anthony, what's the sample? How many movies were sampled to come up with this?
12 movies, the full 2 hours of 12 movies.
Okay.
And so what? I mean, this is. I'm sure you could refine this test, and you can actually, what I really want to do with this is actually go to the next step, which is have this in bins of octaves, so where you actually know what's the average. The point is the center speaker needs to play louder. You need more SPL capability. And, in some cases in the center, there's a thing people don't talk about we're going to get to is it may need better dispersion and coverage because the center speaker sits in the middle of the room, and it could have an audience that's spanning 30 degrees in this direction and spanning 30 degrees in that direction. So over a 60-degree arc, it needs to feed about the same sound. And there's a lot of center speakers, the types that are dual woofers with a single tweeter where the woofers are in parallel, that don't do that. They have very uneven response the minute you move a few feet off to the left or right. So that's probably the most important speaker when it comes to film applications, or multi-channel sound applications in which the center is used heavily. I'm going to pass on this so we have time, but I want to go into this. So here, I think Sean talked about, well, how loud it plays depends on the room. Yeah, if a room's completely anechoic because the client put 12 inches of dense fiberglass all the way around, the fall off from 1 meter to the seat position at least 500 hertz and up is going to be 6 dB per doubling on distance. But thank goodness almost nobody ever does that. That's maybe 0.001% of the population out there. If you do a statistical average of what most people are using for listening rooms or home theaters, and you look at their reflection decay time, just averaging, and I've done that over 1,000 different samples over the years of doing this, and you establish a certain I don't call it RT, I call it reflection decay time over octave bins, and you look at what's the fall off from the 1 meter anechoic value, which we'll get to talk about in a second. You can pretty much consider this, that whatever you measure anechoically in free space, 4 pi, the measured 1 meter sensitivity anechoically translates at the seating position of a 3,000 cubic foot room, which is a 21 by 16 by 9, not entirely coincidentally the IEC standard listening room from, 25, 30 years ago. The value you're going to get at the seating position is 7 dB down. Okay, so if a speaker has a sensitivity, a truly proper average sensitivity, like you guys measured at the NRC of 90, what you're going to get at the seating position for 2.8 volts is 83. Okay, and yep, some rooms will be a dB up or dB down, but it's pretty average. If the room is twice the volume, on average, I'm finding that that ratio of sensitivity or the value at the seat position, you're moving further back, the room's a little larger. It's whatever the 1 meter sensitivity was minus 10 dB. 9,000 cubic foot room, which is 240 cubic meters, it's the 1 meter anechoic sensitivity minus 13. Okay, and you could argue, well, sometimes it's higher, sometimes it's lower. You're right, but what we're trying to do here is to like get to within a target that's a few dB from complete chaos. And for those who don't know, when you apply, this is all based on what would be 2.8 volts, which happens to be 1 watt at 8 ohms.
8 ohms, yeah.
Happens to be, but I don't really care. But if you took a 28 volt amplifier, which happens to be 100 watts at 8 ohms, 200 watts at 4 ohms, the value you're going to get at your seat is add 20 dB. For 200 watts, it's going to be 23 dB. For 400 watts, it's going to be 26 dB. So if you take all of this and mash it together, let me go over here. No. You can run some calculations. I do want to point out, and this is kind of really important because I see people make this mistake in design, is that rooms are reflective. They're not anechoic. The reflections, I think certainly Sean mentioned that. I think Dan mentioned that. The rooms are reflective. There are some reflections. They do support the energy in the room. So the sensitivity at 2.8 volts, which happens to be 1 watt into 8 ohms, I keep saying that, happens to be, is not an anechoic fall off in listening rooms. It's that thing I mentioned before. And I'm surprised how often I kind of have to remind people of that. Now, if you take all of these numbers I said before, and you get a real measurement of sensitivity per the way it should be done, and certainly a good reference would be what NRC did, that's now standards at AES and IEC. 90 dB sensitivity speaker, this is an example for you guys who are watching. Take a speaker that's claimed to be 90 dB sensitivity for 1 watt. You know what? I'm going to change this right now. Hold on 1 second. On the fly for 2.8 volt.
All right, now we're making progress.
Yeah.
And it's interesting because what we're doing with the CEDIA thing is actually even different. You guys will be interested in that. And these are RMS volts. Okay, done, fixed. Let's go back. On the fly. So 2.8 volt put into the speaker, has a 90 dB anechoic sensitivity in a 6,000 cubic foot room. What are we going to get? The at 2.8 volts, which happens to be like 1 watt, you're going to get 80 dB at the seat position. A 100 watt amplifier is going to give you 100 dB. 200 watt amplifier is going to give you 103 dB. A 400 watt amplifier is going to give you 106 dB. Okay, pretty simple. Now, somewhere along the way, somebody who's watching this should go, okay, a 90 dB sensitivity speaker is pretty common. There's a lot of people who make those. That means you're going to have to stick a 400 watt amplifier in this thing so that you don't distort the amplifier on peaks. That's a little scary to me for a basic speaker with maybe a 3-way thing with an 8-inch woofer, a 4-inch mid-range, and a 1-inch tweeter. That just sounds like a lot of power put into a product. And maybe it's okay. Maybe if it can take the burst just fine, it's fine, which is why we're going to talk about bursts in a second. But somewhere along the way with this info, when you're designing a room, you may start to think, my speaker is a little bit big. 6,000 cubic feet is a biggish room. Maybe I need a higher sensitivity speaker. Okay, which some of you guys in this webinar do make. So that's kind of my view around that. Now, let's talk about the what I am sorry. I forget if it was Dan or Scott brought up the peak versus long-term measurement. Can you guys remind me who brought that up? Dan? Thanks for bringing that up. So there are all kinds of overload conditions in loudspeakers. And like you said, is it mechanical? Is it power? Are you actually burning the voice coil or burning a component in the crossover? Actually, people assume that the first thing that's going to burn is the voice coil when you overpower it. But I've actually burned parts on the crossover board for passive speakers at high power. So to be clear, most speakers, not all, but most speakers have a 6 dB difference between what it can take long term. So either sine wave or other signal that just fills it, versus a short-term burst, which can usually go 5, 6, sometimes 7. I've seen 9 dB higher. The interesting thing is most program material has between 10 and 12 decibels of difference between what's in the peak. Somebody mentioned, what is music? What is film? Well, there's typically 12. Sometimes people feel like it's 15, 16, 17, depends on the kind of material. There's a difference. So you do want to know when you're picking a speaker, what's its long-term capability and what's its short-term capability. And I tend to call short-term burst. And the long-term is going to tell you how much power the thing can take long-term and what its reliability. And the short-term is the sense of, what you get in terms of the sense of dynamics. And when it does get close to its overload, what it sounds like is our cones banging up against the backstop. Is something going wrong?
Anthony, so in regards to that, is there a distortion, component to this?
Yeah.
And where would that, are we talking 10% distortion? Are we, I know you're still working on things in progress, but just curious.
I'm smiling because this has been an amazing set of findings in the last year or two. So let me mention this. It's somewhere later, but I'm going to bring it up. There's speakers that I said, yep, I can take 200 watts. That means you can put 200 watts sine wave on it and not blow up the speaker. And it sounds like complete dog do at that point. It's in so far into distortion that you would never ever want to listen to it that way. Yet it can legally take 200 watts into it, which if it's a 4-ohm speaker, that's 28 volts, without blowing up. But you don't want to listen to it that way. So what does matter is what you just brought up, which is like, how does it sound? And there's an interesting body of work that has found that you can actually break those things apart. And I don't know if you guys are familiar with the AES2 measurements or this thing called M noise. And it's an interesting statistical review of that. And I have it a little bit later in the presentation. I'll bring it up. It turns out that if you put a wideband test signal into a speaker that's shaped with a little bit of high frequency droop, so basically flat up to about 1 kilohertz and then a gentle roll off, typically 3 dB per octave, but in which you maintain the peak values to be about flat, and you put that into a speaker, measure its response, and gradually turn it up. There's a point at which the speaker is going to start to distort, but also its frequency response is going to change relative to low level. And the change could be either because of power compression, or because if it's an active speaker, one of the amps is running out of poop, or some other factor. There could be different factors. And what's really interesting with this is statistically, the people who've worked on this have found that if you go much past that, if you start to turn up much past that, the reliability of the speaker goes down and the sound quality goes down substantially. So the work done in a few of the standards bodies that have been working this actually no longer really talk about distortion, but talk about deviation from the original reference frequency response at low level. And first time I heard this, like, what? and then looked into it, tried a bunch of tests, and it's like, wow, that's brilliant. That really does work. And so it's a kind of a statistical review of it. And ultimately, yeah, the speaker at that level should not distort. So where we're going with this is not talk about power or admissible voltage, but actually talk about maximum sound pressure level referred back to 1 meter anechoic and represented in decibels. So don't really care what voltage is in it. It just goes, you can stick as many electrons into this thing and crank it up until it don't want to go no more because it's getting unreliable and starting to sound bad. And that's the maximum sound pressure you're going to get from this thing at 1 meter. And there's a version of that for long term, and there's a version of that for burst. The burst test is it's a different approach. It is actually using Boinker tests, so little pulses of sound that have a bandwidth of about 1/3 of an octave. You crank it up until you see distortion that exceeds a certain amount, and that's where you stop, because anything past that, the speaker is not going to sound good or going to become unreliable. But also,
so Anthony, what happens if a loudspeaker company puts a PTC or something in series with a tweeter and it trips it, and you're not maybe getting the true indication of its dynamic capability?
So if they do that, it's still going to tell you this is as loud as it's going to play, right? The PTC is going to trigger, and it's going to typically what they do usually is they open circuit a resistor, and it's still going to
bring the level down.
It's going to bring the level down, and it's basically as loud as it's going to play. Now, if that thing is very intelligent and it has a difference in its time constant between long and short, well, it's going to tell you on a long term, this is as loud as it plays. And on the burst, it can play louder. And as long as it can play louder without breaking, it's all fine. So up until now, in the residential side, you never knew how loud does it play, and you never knew what it could do long term and short term, and you really want to know all of that to pick a speaker carefully. Now, the good news is on the commercial side, many brands for a long time have been disclosing that. They've been disclosing it using their own method for that. And what we're trying to do within the CEDIA group is go, well, no, everybody's going to be on the same page of these methods. And these methods, the cool thing is that they're easily available. You don't have to build a complicated chamber. Room EQ Wizard has most of what you need in it to be able to measure it. You can download the test signals free, and it's really cool. Ultimately, though, the client, the user, the designer goes, oh, all right, I'm trying to get to this sound pressure level. There it is. So they find out what the 1 meter is. You can measure it at 2 meters and relate it back on bigger speakers, like was done at the NRC, if I remember right. And then you can go, okay, well, this client doesn't really want more than 100 dB peaks because they never, they turned the volume down 6 from the original. You're done. So to me, that's the first look at this thing.
So I have a question, because most of what you're talking about, I think, is passive speakers. And if you have an active speaker, there's all kinds of nonlinear dynamic processing in it. And I'll take the extreme example, a smart speaker where it's small, it's powered, and depending on what the volume setting is, the frequency response will completely change. So as the level increases, the woofer can't handle the power, so they roll off the bass, and it may play a certain loudness, but the quality is not as good as it was at a lower volume. So is that something that has been considered in CEDIA?
100%. And actually, I will disagree with you that this only talks about passive. If the amplifier is running out of steam, or if there's a moving high pass filter, I'm staring at a little JBL speaker over there that sounds amazing at low level. You crank it up, there's no low end, just like you said. And that's not a slight on JBL. It's like everybody has to do what they got to do to make these little things sound loud. That speaker, as you go up in level, at some point, there's a deviation from the original response, right? There's a place where it's more than 3 dB away, anywhere in the band, within an octave band. And that's the max it goes. Now, the fact is it can go louder on a peak basis or a burst basis, but really from a usable range, that data collection will tell you that this is as loud as it goes, staying linear. And so in the case of what you mentioned on these smart speakers, it's an intentional thing to try to maintain increased loudness. In other cases, the limit could just be that the poor little chip that's driving the woofer amp is running out of steam. Whatever the limit is, the methodology looks at all that.
Yeah, because we found when we're doing listening tests on these, depending on the level we choose, we get a completely different set of results.
Absolutely.
Yeah.
Absolutely. And, those are games that people play, like you said, to give a perception of loudness or to protect the amp and woofer from going over the top. And you just need to know that this thing will play up to this level. This is not on the marketing documentation. I'm leaving that alone. I would just assume it. However, whatever somebody wants to write is fine. But when you get to the propeller head document, that's plain vanilla, it's black on white, no design value, just really simple. It goes, yep, this little thing will play up this loud. End of story.
So Anthony, most consumers are going to look at a spec sheet and not really understand the dBs or the hertz or the frequencies.
Yep.
Would it make sense to maybe assign a room size rating to speakers like we do that with subwoofers? We measure subwoofers to say this sub will play X loud and this size room. Why don't we do that with loudspeakers as well? So
in the vision of this disclosure sheet, it would actually, when it gets to SPL capability, long term and short term, it would say the anechoic 1 meter, and then the 3,000, 6,000, and 9,000 cubic foot values. So you don't even have to calculate it. Boom, 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 boom. Sweet. Now, you may not want to play 105 dB in whatever room size you have. You just know, I don't want to play that loud. The challenge with going, this is a speaker that's appropriate for 6,000 cubic feet, is you're assuming somebody wants to play 105 dB bursts. I am partial to going, if you want film reference, this is the size room you can go to, because that's exactly what you're asking for. So I realize we're spending a lot of time on this thing called SPL, and we should, but there's other things I want to talk about. So this is a summary of this methodology, both the AES2 and a few other standards look at it that way. Just turn it up until there's 3 dB difference from reference. That's the max level. That's what it is. Okay, so I'm going to pause there on this, and I know you guys have been interacting with me on this, and I feel like I'm hogging the presentation. But when it comes to SPL, which again, I equate that to picking how much horsepower you want in a car, how fast you want to go. Is there anything else you guys want to talk about in terms of sound level capability, sound pressure level capability? Do you think people should be looking at?
Well, I think the one thing is going to be difficult is for people to understand what they need.
Scott, I can't hear you.
It's difficult for people to understand what they need.
Yeah.
So there's a spectrum of education in the public.
Yep.
That
Absolutely.
Looking at these specs.
Yep.
And if we come up, like a lot of what you've been talking about looks like the CEA 2034 document that was put out. And if you give people that set of stuff, their eyes are going to roll up into the back of their head and say, just tell me which one sounds better, right? So when we come up with these specs, how are we going to satisfy the extremely wide range of need?
Right.
From the most inexperienced, someone who's just getting into it, to the guy who wants to design, somebody's home theater for him. Right. So that's a huge challenge in my opinion.
So one of the things within this is not all about CEDIA RP1, but just so you know, within the CEDIA space, this program has a technical part and an education part, and it's completely understood that as this thing launches, there will be a series of courses that explain, well, what does this SPL thing mean? How do you interpret it? Well, how loud do you want to play? How do you add up decibels? By the way, you guys will find it interesting that amplifiers within that same spec are not going to be revealed as power. In that spec, nothing's going to say this is a 100-watt amplifier. It's going to be revealed in decibels. And at first you're like, what? And it's where 0 dB is considered 2.8 volts, which happens to be 1 watt and 2.8 ohms. I keep saying it happens to be. And then an amplifier is going to be spec'd as something that's a 30 dB amplifier. Its capability is 30 dB. If you take a speaker that's a 90 dB sensitivity and you put a 30 dB amp on it, what do you get? You get 120 dB, just adding that on, as long as the speaker can take it, by the way.
And there's another place that tells you just adding up the dB to where
just add dB. And then you go, okay, well, so that's at 1 meter. I'm in a room that's 6,000 cubic feet. I take out 10. So that dB, that speaker with that amp, can give me think I may have lost track of where I was, but maybe 110 dB. Was that still there? 120, 110. Yeah.
So you have to specify the impedance when you say that dB number, because no amplifier is an ideal voltage source. It might be 30 dB at 8 ohms, but it might fall apart at 4 ohms, right?
Absolutely. And it is actually at 2 ohms, 4 ohms, and 8 ohms.
Sweet.
Right. And so we're going to talk about impedances a little later. Gene, how much more time do we have?
It's all up to you guys, how much energy you guys have. I can keep going. If you guys want to keep going, we can keep going. I think speaker impedance is another important one. I know Scott and I have spoken about that in the past, and I'm sure he has some thoughts he'd like to cover on that as well.
Right. Well, the thing I have queued up is a spectral response, which to me is huge. It's all over the board. So let's cover that real quick. What we have right now that affects the overall I call it spectral response. The term frequency response is colloquial in a way, but it's a spectral response of a speaker. If you look at, again, I'm pretending the same thing. You just downloaded 20 different sheets from different manufacturers, and you try to find out, well, what's the frequency response of this thing? It's going to most often tell you frequency range, and that's about it. It goes, the speaker is good from 45 hertz to 22 kilohertz. Is that enough? So I'm going to open it up to you guys again. Is that enough? Do we need to do anything more than that? Or is that good enough for a person to pick that, speaker A versus speaker B or C? Any thoughts, anybody? Should we go around the circle again, starting with Shane?
Well, yeah, again, more information is going to be helpful for people, but, frequency response, I think that, especially as it pertains to theater systems, it's interesting how many customers end customers I talk to where, they still don't even understand the basics of where a crossover needs to take place between, let's say, your main speakers, which oftentimes are larger, maybe tower speakers, and a subwoofer, in order to give you, the ideal integration between the main speakers and subwoofer, and give you the ideal maximum, I should say, dynamic range in a system like that. So, yeah, I think, specifying what the actual bandwidth is of the speaker, and it's where it's really going to be used. Again, going back to, a large tower speaker, oftentimes people are, naively or not, limiting the use of that to just the top mid-range and tweeter, aren't even really using much on the bottom end, and that may be a good thing, because you're letting the subwoofer do what it does best, and you're not straining the speaker, the main speaker's low frequency drivers. So I think there could be more discussion, more. I think consumers need more help trying to determine just what's really needed from that perspective.
Oh, somebody's got an EBS test going on.
An emergency broadcast.
Yeah.
Flood.
One of my first jobs while in college working for a radio station was to fix the EBS receiver. It turned out every single electrolytic capacitor on that thing had dried out. That took forever.
So,
okay,
let me state one more thing. So, with regards to frequency responses, I know you're going to get to directivity, but within that frequency response, plus or minus 3 dB, which is what we typically hear in the industry or consumers do, and the power response, as you said, and how that the frequency response and power response are related.
Right. So again, what I see in most cases is not a frequency response chart on consumer product, not commercial or pro products, where they actually show you an actual curve. Most often I see a thing that says frequency range or frequency response, and it just goes 45 to 20K, and that's it. Maybe they'll say -6 or -3, and you don't know what that means. So, all right. Any thoughts, Dan? Going around,
sure.
what are your thoughts? Is that enough? Should we worry about anything more? Is that enough guidance to pick up?
No, I think it's great. And I think as we're talking about individual points and then we're moving on, but really, I think a great way to look at it is all these points are critical components to making high fidelity, right? So if we just isolate, that single point SPL we were talking about, that doesn't clearly define it. And then, so we broaden that to, a sensitivity over bandwidth. And then we talked about peak SPL capability and then alluded to underlying distortion. So that brought us a long way already. Now what's the next important that's tied into that? So now you have a high sensitivity, high peak capability speaker. What's the bandwidth? What is it capable of? Low frequency, high frequency, what are its limitations? And then, of course, how is it reacting? I call overall, you called it spectral, power response, polar response, those type of things. How is it going to interact into the room? So now we're getting into all those really, really important factors where that single curve frequency response wasn't enough to define it. Now we're talking about what is it doing maybe over the listening positions? Was it doing with early reflections and then the total sound power? So there's a lot in there, but all that is extremely important in defining the fidelity and defining how it's going to react in a room. And also it will help define how one speaker will be a different choice than another in that room or that size room, or even just defining fidelity for that person, right? So you might have a lower bandwidth, less sensitivity for either a smaller room or a less demanding listener.
Right. So you mentioned something really important, which is both the fidelity of the speaker and how it's going to react in a room. We listen to speakers in rooms, and there's something in the data that we're going to talk about that helps you know how that's going to work. Sean, any thoughts on this? Again, the question I keep asking is it enough to just have a number that says 45 to 20 kilohertz, and if you're lucky, -3 dB?
No, I mean, it's completely useless by itself. And it just guarantees the speaker will make sound. And it's like going to the doctor and you've got a health problem. He says, well, what's my prognosis? You're alive. So... and there's been 40, you have a pulse. There's been 40 years of research into this topic, and it's been shown that you need a complete characterization of the direct sound, the early reflections, the late reflections, the sound power, and it's if you have that information, you can predict with about 86% accuracy how people are going to rate its sound quality, and it's captured in a ANSI CA standard 2034. It's part of the Klippel scanning system. So, I mean, we need to move forward 40 years and start specifying comprehensive response measurements measured on different angles and the sound power. So the science exists, and the fact that we're still putting a single number, headphones is the same, all headphones, it says 10 hertz to 40 kilohertz. And you get a high resolution Sony sticker on it if it goes to 40K, but there's no tolerance on it. So it could be 60 dB down at 40K. It could be a horrible sounding headphone and get that spec. All it's really done is sold more 1/4-inch microphones because you need a small microphone to measure that high.
And if I could interject one thing in there that Sean kind of alluded to is, what's the -3 dB point or whatever, if we're talking low frequency, well, also what's the slope of that roll off and how, because that also talks about how that speaker is going to have low frequency performance in a room. If it's a shallow roll off versus a really steep roll off. There's a lot to that.
Absolutely.
And even, I mean, a tolerance is great, but plus or minus 3 dB, you could have, it could be flat, it could be tilted, or you could have resonances plus or minus 3 dB. It's going to sound horrible. So it doesn't, like I said, it's like going to the doctor and saying you have a pulse.
Right. So by the way, if you tried that, go get a bunch of different manufacturer spec sheets, you'll barely ever see plus and minus 3 dB. You'll see a frequency range, and if you're lucky, a minus 3. They're just basically telling you where it's moving out, and you have no idea what's happening in the middle. Yeah. There it is. That's just, and you're right. 40 or more years of engineering has said we need more, and it's just not there yet. Yeah. Scott, any thoughts on all of this? Is it enough to say 45 to 20K or
yeah, you're not going to characterize the sound of the speaker in a couple of numbers, right? That's just not going to happen. And so at least you're getting bandwidth, I guess, if they're using some sort of standard, like in a lot of our stuff, we do put the 3 dB down points, which gives you the basic bandwidth. But even if we put plus or minus 3 dB, like Sean said, I can make 100 different speakers that make the same spec, and they'll all sound completely different, right?
Right.
So it's not really all that helpful in telling you what it's going to sound like.
Right.
So just having an on-axis graph is a nice leap forward and tells you a lot about the loudspeaker. It doesn't tell you everything, of course, but at least
it starts to tell you
that's the next step. And then obviously something like the 2034, the spinorama test, and so on and so forth. But even that, in my opinion, isn't enough, especially when you get into the higher performance. In other words, again, we're back to the application. If I'm looking for the highest performance that I can get, it may sound best at 5 degrees off axis. And if I don't have that curve, I'll never know it, right? Just because, let's say, diffraction, calms down enough at 5 degrees that it sounds much better at that. And, maybe I don't care about the early reflections and sound power enough because I can afford to treat my room, right, or whatever. So, putting a couple numbers, I can tell you some anecdotes from our marketing department when I'll send them the specs and they'll say, okay, why are these two the same or nearly the same? And, this one's $200 more than this one. And my patent answer is because these numbers don't tell you what the speaker sounds like. But, these people that in the marketing department are very similar to the people who are buying the product in terms of their knowledge of how this works. And so if they're asking that question, the customers are asking the same question.
Correct.
Right. And so this is where you get into this problem of, and we've been running into this at Polk with the last few lines we've put out, is we're getting punished for telling the truth. And when we get into impedance, like Gene said, it's like we went and told everybody they're 4-ohm loudspeakers, basically by like the AES definition of impedance. And people are going, oh my God, how can you guys make 4-ohm loudspeakers? Everybody else is 8. We're like, nobody is 8. They're all 4-ohm loudspeakers. There's a few 6 maybe by some definition, but you wouldn't believe the amount of, heartache we've had or complaining when we go out and tell the truth.
Right.
Well, maybe manufacturers should be forced to say these are engineering specifications.
Well, there you go. The problem is there's no enforcement of any kind. The only thing you can do is hope that reviewers or somebody comes out and says it. But how many customers are going to see these reviews or any of this stuff before they go and buy a speaker? Not all of them. Certainly, if half of them, maybe you're lucky. It's like a very small percentage. It's the enthusiasts that are going to go.
Gene has an enormous following. An enormous following. He's very transparent, sometimes as offensive to marketing departments, but he says it like it is. And within the CEDIA community, which is a very small community, we are trying to standardize the disclosure of those things so that the client who's relying on their expert to pick the right thing for them, that expert has real data. Right now, they don't have data.
But Anthony, there already is a standard for specifying loudspeaker impedance. The IEC standard, again, you got to be 80% of the nominal rating within a free 300 hertz to 3 kilohertz or something like that.
There is, but how many really conform to that, I think, which was said, is a good point. And so maybe having manufacturers have to state for instance, the minimum impedance of the speaker as well as the nominal impedance rating.
Yep.
Good idea.
So that's
but nominal isn't even defined
Well,
for most of these things. If it's got a minimum of 3 ohms and you're calling it 8 ohm loudspeaker nominal, then nominal has no meaning.
you're right. If it doesn't conform to that,
that's sort of against the law, but whatever. So I hope we have time to get into, I'll keep talking as long as Gene doesn't cut off. I do have a whole section on impedance because it is important.
How are you guys doing? Do you guys want to,
issues.
do you guys want to go a little longer? You guys okay?
Yeah, I can
I'm
probably do
okay
15
for another
minutes.
15, 20 minutes.
We
Sounds
got 15
great.
minutes,
Sounds
Anthony.
great.
Solve all the problems in 15 minutes. Go.
So it sounds like we all agree that frequency range, which doesn't even say response, is not enough. It doesn't tell you anything about why you should spend $600 instead of $300, $1,200 instead of $600, etc. And so then what's needed? And really, Sean hit on it, and you guys are all aware of it, is all of the work that has been done for 30 or 40 years, and standards out there, and things that are already disclosed in the commercial and pro audio space. So let's just bring that into our world now. If I can get back to the presentation. So we agree. I'm still sharing that, right?
I thought you lost your audio for a second. Oh yeah, let me get you back on. Hold on.
All right. So we agree that frequency range is not enough. So then what do we want? And here's my little spiel on this, and I'll try to do this in 3 or 4 minutes. So overall, there's a overall concept of sound power that is the combination of wanting a speaker with a smooth, what's called axial response, or whatever is the listening axis. Scott, you correctly said that the listening axis is not necessarily right in front of the speaker. It could be that the design for that thing is 5 degrees off or 10 degrees down. There's a bunch of speakers that, for all reasons that are what they are, that are not made to be listened to straight in front. They got to be towed or whatever. So the idea is to try to find out what is an actual curve of the amplitude versus frequency on axis, as well as in a number of different curves. I think overall the sound power does matter. The off-axis response does matter. And here's why it matters. And this is the thing that I always want to bring up in these sessions where we talk about off-axis responsive speakers and room acoustics. People don't realize what I'm about to show. So you take any good speaker, you're going to listen to its direct sound. Okay, that's the blue line. It's going to feed some sound pressure, like we talked about. There's going to be a certain value at 1 meter or 2 meters, 3 meters, and that's what you're going to get. But then along with that, there's some reflected sounds, which I'm showing here in red. One that may be 10 degrees off axis, passes your head without hitting you, and bounces around a few times until it finally gets back to you 50 or 60 milliseconds later. There's another axis, because speakers are not just little arrows of sound. They actually spread sound out over a pretty broad range. There's an axis at 20 degrees off axis. It's going to bounce around and then finally pass your listening area and enter your ear canal, and so on and so forth. And that's all the off axis sound of a speaker. Kind of like a light. You put a light bulb in front of you, and some of the light goes directly to you, and a bunch of it lights up the walls, like all the way around here, unless you have a big lens and a reflector in the back, which people don't usually make hi-fi speakers that way. So here's one direct sound. Here's some reflected sounds from the right wall, and as you can see, in this simple schematic of only the horizontal and only in 10-degree increments, there's a lot more red arrows than there is a blue arrow. And then you add in the left side, and there's a whole other thing. And just on this horizontal plane, I'm not even talking vertically, just on this horizontal plane, there's a lot more return from the room than there is direct sound. Now, it is true that the red arrows are attenuated by either off-axis variations of the speaker. They may get quieter. They're attenuated by the fact that the path is longer. They're attenuated. They have to bounce off a wall and lose some energy. But all together, all those red arrows in this really simplistic representation of sound power add up such that in an average listening room, there's about 2 to 3 times more net sound energy coming from all the reflections than there is from the direct sound. In most rooms, in most typical listening rooms, that would be maybe a living room that has, like Floyd calls it, the stuff of life. So couches and carpets and maybe a drape, maybe some bookcases and stuff. At about 6 feet from the speaker, 2 meters from the speaker, the level of the direct sound is right around the same as the level from all the reflections. It's known in large room acoustics as the critical distance. Doesn't quite apply in small rooms, but that's the place where that direct sound and the reflected sound is the same. That's only 6 feet away, 2 meters away. As you go further away from that, you have more reflected sound. And that means that the quality of those reflected sounds, those off-axis sounds, matter a lot to what you hear in terms of pleasant character, not just the direct sound. Even if you put some acoustical treatments in the room, if you assume you don't want to over damp the room, so it's an anechoic chamber, if you assume you still want some liveness in the room to get to the standards that actually the NRC came up with, 35 years ago for the standard listening room, and then the work that Eureka did to say, look, this is a desirable target reflection decay time. You're only going to absorb about 15 to 20% of the surfaces, so there's still a lot of reflected energy in the room. That sound power should be smooth. So I'm a big fan of finding a way to disclose to people, here's the axial response, here's the off-axis response, and here's the sound power. Well, guess what? I'm not the first guy saying that. So you guys did mention the various standards, the ANSI CTA 2034 and what's called the spinorama. So what we want in deciding a good speaker is something that has good axial response, or whatever is defined as the listening axis, and there's still errors there. I see speakers that are expensive come right out of the box and their axial response is horrible. And then much harder is speakers that have smooth and continuously smoothing off-axis response. That doesn't mean it has to be the same level, but the overall spectral balance really should be the same, so that what's bouncing around the room is even. And all of that can be represented in the spinorama style. So we want smooth off-axis, we want smooth on-axis, and it should all look good. So this is an axial response, this is an off-axis response. The two should be within a certain reasonable variation. Now, let's talk about this spinorama thing, which I've now mentioned twice, and I think, Scott, you may have mentioned, and Sean, I think you mentioned, right? Spinorama, I think, is also a thing. Didn't Floyd coin that term? I think
someone at Harman did. I'm not sure if it was him or him.
It sounds very much like a Floydism. It's like right down the level of his sense of humor. But you take a speaker and you measure it over 70 points in two circles, one around the waistline and one around the head to toe. You get all this data, you average it all a certain way, and you represent it. I'm going to move forward here. You represent it this way. I got a chart that's coming later, but I'm going to start with this. You put it out to the clientele where you show the intended axial response in black. You show what's called a listening window response, which is an average over where listeners are typically going to be, which is 30, 20, 0, 20, 30, 15, 0, 15, 30, and then plus or minus 20. That's an average of the listening window. You show what the early reflection energy is, which is what's going over to the walls and the ceiling and floor. And then you show what the net sound power, which is the average, the spherical average all the way around a room. And if you know how to interpret this, because you've either been to one of the courses or you just read a little bit, you go, I can see this is going to be a decent speaker. I can see that this is going to be a decent speaker. I can see that this is maybe not going to be a decent speaker, and I can see that that's really not going to be a decent speaker. That's based on theory.
Those look familiar.
Those are
familiar curves to me, yes.
And you know exactly where I got those.
And I can tell you the scores in listening tests. Yeah.
So let's look at the scores. So there's a place here that says, okay, do these measurements matter? So here I am talking like a propeller head. I'm talking math, physics, all this other stuff. Come on. If it sounds good, it's good. Well, is that true? Is there a way for you to look on a piece of paper or a downloaded PDF you're looking on your screen and go, that speaker is going to sound good. That speaker is maybe not going to sound so good. That one doesn't cost so much. That one costs more. Now I see why I should spend $1,000 more on this one. Does it matter? So Sean and Floyd and many other people that worked around him spent the time to measure these 4 speakers and make a bunch of listeners listen to them in a really amazing room in which you can put the speaker at exactly the same place behind a black screen cloth. You don't know what you're listening to, but you actually score it. You go, I like A better than B, whatever. You do a bunch of tests. I forget, was it 20 samples, Sean? You remind me?
20 samples of music or 20?
You would go through all the shuffling and how many listening samples would you do? I forget now.
Typically 3 or 4 different music samples, and then we do a repeat of each trial.
Right. And so in this series of tests that Dr. Sean Olive and Dr. Toole and other people did, over 300 different listeners, I actually participated in some of those. Here were the scores. Model A, everybody liked better, slightly better than Model B, that liked slightly better than Model X, and liked slightly better than Model Y. And guess what? Model Y was the one with the rattiest response. Model X is the one with the slightly less ratty response. Model B is the one that looked pretty good, and Model A is the one that looked excellent on this theoretical set of tests. So this is just one example of 4 different speakers. This has been repeated on many speakers. And basically you can show that with pretty high certainty, if you can make a speaker that displays correctly on these spinoramas, which has a certain character to it, chances are most people would like it. Interestingly enough, some people like this better. That's how statistics are, right? Some, there's curves, and some people like this or that better, but the majority of people liked that better. And there is a correlation of 0.86 between the measured response and the preferences. So if you're the designer of a theater or a listening room, and you got to pick some speakers that you want to have an 86% certainty that your client's going to go, thank you very much, here's my check, I love you, they kiss you on the forehead and they call all their friends because you're so cool. You'd listen to this if you want an 86% certainty. As far as spectral balance, you just got to follow the spinorama concept, which is make sure you pick speakers that show on these charts a really decent set of results. And there's other people who like it a little bit better this other way or this way, but 86% is, I'll take it. So there again is the spinorama approach, where there's an on-axis response, or whatever is the stated axis. Like Scott mentioned, that stated axis could be 5 degrees off this way or up or down or whatever. The average window response, the early reflection zone, and then the sound power. And if those things all look like reasonable carbon copy of those, maybe turned down, maybe at low frequency, they converge. And if you know how to look at this, which we're about to talk about directivity, you can actually pick the speaker for the room, for the client, that is on paper they're going to like. So so any reactions to this? I think this is all common knowledge to you guys, right?
Yeah, Anthony, I would though just bring up the fact that depending on your room, because we know the room is half of the battle for good sound. And I am of the personal opinion that a speaker with a very flat frequency response on axis, but maybe a higher directivity index in a typical room that's usually unless it's a dedicated listening room or a theater room where it's been properly treated, oftentimes that speaker that has, again, very good on-axis response, but maybe higher directivity index, and so maybe not as even off-axis response, oftentimes sounds actually better because the ratio of direct to reflected sound is higher. So
correct.
How do you account
for
that?
There's nothing in this that says you can't have directivity index, and I'm sure glad you brought that up because that's the next slide that's queued up. You can do all of this and have a high directivity index. You can have a speaker in which the difference between the axial response and the sound power is deeper, as long as the sound power doesn't look like this.
Correct.
And that's the whole idea. I guess it used to be called constant directivity. And you can have a high Q, constant directivity, or a low Q, as long as what's going off to the walls is not all, chaotic, you'll end up with good sound. And you're right. In some rooms, you need more directivity. In some rooms, you need less, as long as it's a evenly and constantly controlled. Somebody else was saying something. Sorry.
I think it was Sean.
Gene, I'm aware that we should be cutting off soon here.
Yeah, no, I was just going to say, I mean, that's the same thing as saying if your off-axis response is really bad, you can either fill the room with fiberglass and absorb it, or make it so low in level that I guess it'll contribute less to the overall impression of sound quality. Is that right?
And well, go ahead, Anthony, if you were going to.
No, I was going to say, so there are different opinions and tastes on those things. And there's a lot of papers written on this. I have my own opinion based on the speakers we're doing, which is like, you got to have constant directivity, and you want to light things up as evenly as possible, because most people like that and it sounds really good. But it does depend on the room. You are right. So in parallel to all this, there's another standards group called RP22 that within CDS teaching people, well, how do you treat a room so that the combination of a speaker and the room work together well? And there's some recommended practices for how much absorption and how much scattering you put in the room, where you put them, so that in the end, it all works nicely together. There's no doubt that a big room that's going to have a longer reflection decay time and may not be able to be treated too much because of aesthetic reasons is going to need potentially a different DI, directivity index, than a smaller room. But right now, nobody's telling anybody what the DI is. And where I'm trying to go with this is a discussion that goes, yeah, well, let's tell people what it is. Again, on the commercial side, you can find all of this. These charts I just put up, there's a bunch of products you can go download right now, and you'll see the spinorama curves, you'll see the directivity index. And if you know how to design with that in mind, you can do a great job for your client. In the residential side, it's like crickets. So, Gene,
so what about the...
Sorry,
I was going to ask you, because there is another school of thought where narrow directivity or narrow dispersion speakers will give you a wider sweet spot because of the time intensity trading. So if you put the speakers further apart and angle them in, and then the off axis gets quieter. So as you get near one speaker, you hear the other speaker more, and it gives you a wider stereo sound stage. I don't know. Is there something to that, or is there something to maybe having a speaker that's DSP controlled where you could kind of program the directivity depending on the room acoustics?
Yeah, all of that does exist. So I'll start with the latter. DSP controlled directivity is available in the commercial space. There's all these line arrays with varying widths of lobes. They always have some ratty responses as you get close to the top and bottom. Also, B&O, Bang & Olufsen, makes a speaker in which you can change the directivity based on your use. So that's around. And then when it comes to the time intensity trading, I do want to remind everybody that it can take up to 10 decibels of extra level to overcome a 5 millisecond or an 8 millisecond difference in arrival time. That's huge. And so you gotta, it's complicated. And there's different approaches and schools of thoughts that are practiced by different people. And I'm not saying there's only one way to do it. I'm saying let's disclose, and let's disclose in an even and concerted way. You guys, I think, are all agreeing. Let's tell people. So the next thing I have up here on the slide deck is directivity index. And I know we're totally out of time. Gene, you probably know how many people are still watching, or if we should just cut off here and talk.
It's still pretty steady, but I know everybody's kind of getting tired. It's a Friday, and I invite all of you guys to come back and do a continuing discussion on this, especially as we get closer to releasing that standard that we can't mention.
Yeah. So
hopefully it happens.
No, we can mention there's a standard. I just can't go into too many details. Even talking about the fact that we're going to relate everything in decibels is already kind of going a little far. It makes things easier for either the consumer user or the designer. So let me just bring up directivity really quick, since Shane brought that up. What do we know now in directivity on consumer specs? Basically nothing. Go look up and down 30 different consumer speakers, and nobody's going to tell you what either the directivity index is, or the Q factor, or I don't know, whatever that tells you, how wide or how narrow of a dispersion it is. And we need it. Ultimately, it's an important thing. It's an important thing because you have more reflected sounds in a room. You know, speakers are not pulsating spheres. They have some varying directivity. At, you know, typically low frequency, they're wide dispersion. Mid frequency, they go hemispherical. At high frequency, they can go quite directional. And it's important. It does change completely how you listen to the speaker, and you want to look at it. So ultimately, if you can actually look for products that have this disclosure that shows, again, the axial response, the listening window, the radiation that changes with frequency, and the sound power, and this blue curve right here, this here is essentially a comparison of the sound power to the listening window, and it shows you what's the directivity in this room. And this is a speaker that has a gradually rising directivity. It doesn't have any big accidents. It goes up quite a bit at the top end where, you know, most people are not necessarily going to notice it. But this is a speaker that in, you know, most of the operating region is going to have a DI, I'm going to say about 8. And then you can make a speaker that has a DI of 12 or 15 that starts evenly at the bottom and rises up smoothly and is nice and smooth all the way at 12. That's going to tell you it's going to sound good, and it's going to be directional. You're going to have more direct energy. It's going to be more articulate, but it won't vary so much from room to room. I think one of the biggest things that happens when you have speakers with wildly varying sound power or directivity with frequency is in one room they sound one way, in the next room they sound different, and you're chasing your tail trying to tune them. So that all of that's extremely important. Dan, thanks. Excuse me, Sean, thanks for bringing that up because people need to know that they're looking for it. So there's a whole bunch of things here about concepts of directivity and how you get it, and we're not going to get into it because we don't have time. I would recommend that we just table this for a future discussion.
For sure. And, you know, I could put this slide presentation on our Patreon channel. So if any of you guys that are patrons on Audioholics, you can access it and you can see more. Anthony put a ton of work into this slide presentation. In fact, Anthony, we should probably do a follow-up in the coming weeks. Any of you guys that are here now are welcome to. I could send an email, and whoever wants to participate, you're more than welcome to. And I just want to thank everybody that's here. Shane from RBH, Dan from Perlisten, Scott from Polk, and Sean, of course, from Harman. Appreciate you guys spending the time here on a Friday. I know everybody has better things to do, but it's always awesome to carry the audio knowledge forward. And hopefully we learn something from this and we can get better specs in the future. And Anthony, again, a million thanks to you for putting this all together.
Thank you so much. I'd love to do this again some other time with the rest of you guys. Just take it from here and keep talking about these things. Also, both for the viewers of this, but also to help us out with Insidia to refine this disclosure specifications. I want to be clear. We're not specifying anybody how you got to build a speaker. We're just specifying how you disclose what you got in your speaker so that people can choose wisely.
Yeah, absolutely.
Yeah. I mean, I think another topic of discussion would be, will consumer manufacturers actually ever publish this stuff? I mean, why aren't they doing it now?
Actually, I found out why. Yeah. Because the marketing department, what was it? Mike Watts, your guy, goes, I don't need to tell them. They don't know how to understand this. I'm not gonna waste any space. And so they don't publish it because they think that people don't want it. And because people never see it, they go, I don't even know this exists. Yeah. So, and the case in point, again, I'm going to keep bringing it up. Harman products, as well as Sonance products, as well as many different people's products on the commercial side, they do disclose all of this stuff. It's there. And it's there because people know what to do with it. You know, the professional engineers on the commercial side who have to design for specs, sometimes it affects safety and life safety, where somebody's life could depend on it. They know how to design with this in mind, and they would not dream of speccing in a speaker where they can't see all of this stuff. So it's a bit of a sea change. It's a bit of a heavy lifting, but as long as we start by going, okay, here's a voluntary set of disclosures, and then CDM members, here's a class you can take about it, and then consumers, here's some webinars, some live streams that I think Gene should put out that can go read about it. Then within a year, you'll actually see a sea change of this. Thanks for bringing that up, Sean.
And Anthony, at the very minimum, I think the industry should be more transparent on loudspeaker impedance and, minimum and maximum kind of power you can put into the speaker. So people can put together, even someone that's not extremely knowledgeable can buy this speaker and that amplifier and put it in their room and not blow something out or have too much distortion. I mean, we should at least have very basics. I know if you throw too much data at people, it overwhelms them, but I think a very minimum basic like that is useful.
Yeah. If we got 2 seconds, I actually want to, I'm talking about these spec sheets. Can I just take 10 more seconds to actually show you some real life examples that's actually started this for me? The real story that got this really going for me was I was asked to do a design of a commercial space using SpeakerCraft speakers, and realized, they make commercial speakers now, cool. But wait a minute, on the commercial side, I get all this data I don't see on the residential side. So this is the case in point. Here's the data sheets for 3. These are older speakers from SpeakerCraft. Everything we just talked about. Frequency response. Here they actually gave us a plus minus 2 dB, if you believe that. So here's the specs on 3 speakers from SpeakerCraft on the residential side. Here's the same specs for the same 3 speakers or same 2 speakers on the commercial side. Look, there's a lot more. And then there's also polar plots and frequency responses and impedance curves and off-axis responses. Same speakers. Continuing on, here's actually a venerable, very good old commercial speaker from JBL. Look, you guys can't read all this, but there's a ton of really good information here on the first page. On the second page, look at this. Beam width, responses, directivity index, frequency response, impedance curves, off-axis responses, and then a bunch of dimensions. So this is out there. This is the speakers we're making. This is what we disclose. And so that is out there. I guess my dream, can turn that off. My dream is to, like Sean said, let's bring this into the residential side, at least in the CEDIA space where systems are contracted and engineered so that people can do a good job. And in a way, CEDIA is going to be depending on you guys. I'm going to depend on you guys to measure these things and disclose them according to the specs that are not proprietary to CEDIA. There's industry standards out there. The disclosure, though, would be consistent. So whether you look at one brand, one product, and another one, everything's always in the same place, very much like the way it is on foods. So I'm going to bring up my favorite food, of course, which is chocolate, which has no nutritional value. I'm sorry, I ripped through it, but you guys know that on the back of all these foods, there's actually what's called nutrition facts, right? And so, and Gene, maybe on the back of your box of chocolates, there's that too. And
for sure.
My little vision.
I ignore it, but
ignore it. Yeah,
certainly ignore it. My vision is just that whatever amplifier, speaker, projector you're using, it's always disclosed in the same way, and it always follows the same measurement method. If there's something you don't want to disclose, just don't disclose it. It's fine.
Yeah, agreed.
So that's the idea. So that's, I have a dream. I hope that someday we'll see all this data on consumer products.
And the other thing too is if manufacturers disclose their frequency response data in a similar fashion, it would give us ammunition to put into a processor so we could do better room correction. So we know what we're correcting for. Right. We're not correcting for the speaker problem, or we're correcting for the room problem. It's easier to differentiate that, I think.
And Scott's, in this dream, Scott's problem of talking to the marketing person goes, these all look the same. Well, now I've got more data I can disclose that show why this product is $200 or $300 or $500 or $2,000 more, because look, it's got all this other stuff that works better.
I can think of two ways to increase the participation in such a program. The main one is demand. 2034 has been out for some time now, and so is CEA 2010 Loud and Low. Hardly anybody publishes any of that data in any way, right? So it's not a lack of standards. They're out there. They've been out there. AES has had loudspeaker standards, IEC standards forever. The reason they're not published is because they don't have to publish them. Nobody's asking for them, right? I mean, I can tell it's very rare when I get calls from customer service where somebody wants to know the crossover frequency or slope of something. Most of the time people are just whatever, there's just no demand for it.
Right.
So creating that demand is one way to do it.
Right.
The other one that I've been kind of prodding with is there are a lot of people with microphones now. everybody and their brother can go out and measure frequency response and maybe even some, off-axis stuff. The big problem there is not all of them know how to do it properly or can do it properly. So if a manufacturer gets their stuff measured by somebody, that person publishes their results and it's wrong, or it wasn't done properly, but that's the only data that's out there on that product.
Right.
So the manufacturer would be better served by having that, like here saying, this is what we measure, this is what we think it is.
Yeah.
So those two sides of the
Right.
equation will help to increase the amount of people that are going to publish that data. Now, there are some companies that I can almost guarantee you will never do it.
Yeah.
Right.
It's interesting in the headphone space, which I've been focused on the last couple of years. You go to a headphone show and there's all these young people and they're very technical. They're buying measurement equipment and they all want to know how it actually measures because they're really into equalizing headphones. They take the measurements. There's all kinds of sites that publish measurements and they design EQs, which they download into their phones. So it's totally opposite of loudspeaker people in that they're really thirsty for good measurements.
Well, and a lot of headphones, very, very few of them sound okay on their own. They need EQ.
Well, we're 20 years behind. We didn't start doing research until 8 years ago, and speakers, like 40 years, they did research 40 years ago.
Headphones are coming a long way fast.
Or more. So Scott, all points well taken. Like I said before, Gene has an enormous following. You know how many people are actually watching his live streams. And I'm going to put pressure on him. He can disseminate this information. He can make, a series of little webinars, maybe with us all involved. We can start a movement over here. The French Revolution wasn't started out of nowhere. Neither was the American one. A few people got together and said, we're going to change this. And it's in our power. And in the end, it's not about forcing everybody to make perfect speakers. You can't afford it. There's got to be a whole range of things. It's just helping people realize what they're buying when they go from $100 to $500 to $1,000 to $1,500, etc. And how to pick, and also how to pick the right functionality for their room. Because quality is one thing. We keep talking about quality, but there's also functionality. You may need more or less directivity for your application. And how do you do that? Gene has the capacity to educate a very broad group of consumers to this. And within CEDIA, we have the capacity to educate the integrators so that they learn through the coursework, what all this is about, and we can just make it all better.
Anthony, I'm just thinking you could be the Alexander Hamilton of the industry for us. Just don't get shot.
Yikes. Yikes.
I just want to add one more thing. I think which will help manufacturers publish measurements that are meaningful is that the audio retail store is like disappearing, or it has disappeared, and people don't go out now because of COVID. So you can't actually go and listen to a product. So if there's really good perceptually meaningful specifications that relate to sound quality, I think there'd be a huge demand.
Yeah, absolutely. That's a very good point. You want to be able to buy on spec and know it's going to work right. And with the work you guys have done at Harman, you've helped propagate that, at least in the professional side. And now we just have to bring it to the consumer side and the custom install and consumer side.
Awesome. All right, guys. Well, this is a wrap, I think. Everybody needs to probably go eat dinner or whatever. It's Friday night. So again, I appreciate everyone being here. Guys, don't forget to hit that bell notification, hit the subscribe button on our channel so you can get more access and you can get notification as to when we do these live streams. I'm committing everybody in this panel to come back so we can continue this discussion, because Anthony put together a slide presentation that's like 120 pages, 120 slides. We went through about 6 of them. So we've got a lot more to cover, Anthony. So
count me in.
Awesome. All right. Once again, I appreciate everybody being here. And until next time, my friends, keep listening.
Enjoy the ride.